Welcome to Bonding Review Part 3. This one's all about intermolecular attractions. So what are intermolecular attractions? They're also called intermolecular forces. These are the attractions that exist between particles, usually molecules, that essentially hold the particles together. There are several different forces of varying strengths, and we're going to talk about all of them during this review. The intermolecular forces are much weaker than the intramolecular bonds that hold the atoms of a molecule together. So here we have an example of water. The bonds between the O and the H that are within one single molecule are referred to as an intramolecular or covalent bond. The attractions that occur between the O of one molecule and the H of another are the intermolecular attractions. Specifically, this is called hydrogen bonding. This is not a set bond, unlike the ones that are in the covalent bond. Why are these so important? The relative strength of the intermolecular attractions in a sample relates to many of its properties, including boiling point, vapor pressure, and melting point, among others. So here you have a little graph of boiling point dealing with a whole bunch of different molecules. We'll discuss why they have these trends a little bit later on in this review. In order to talk about intermolecular attractions, we have to talk about the types of molecules using the VSEPR theory. There are two major types of molecules, polar molecules and nonpolar molecules. Polar molecules are called polar because the molecule has an uneven distribution of charge resulting in the formation of a dipole. This depends on the shape and makeup of the molecule. If the molecule is asymmetrical, it will be polar. Nonpolar molecules are called nonpolar because the molecule has an even distribution of charge resulting in a neutral molecule. There may still be polar bonds here, but if the shape is symmetrical, the bond polarities will cancel each other out, resulting in a nonpolar molecule. Now, a dipole, back to polar, is when there's a positive end to your molecule and a negative end to your molecule. This does not mean they are creating ions, just that there's an uneven distribution of charge. The polarity of molecules is on the spectrum. Things are not either polar or nonpolar generally. There are degrees of polarity, and the substances may be considered nonpolar in one situation and the polar thing in another, depending on what they're being mixed with. Remember, solubility is very dependent on polarity, and polar things are miscible or will mix with other polar things, and nonpolar things are miscible with nonpolar. But again, this is on a spectrum. So something that could be considered polar may still mix with something that's nonpolar as long as the nonpolar item is a little bit polar. So it's all on a continuum. So here we have some examples to practice determining whether a molecule is polar or nonpolar. I'm going to ask you to think about both the bond type and the molecule type for these examples. Remember, bond type is determined by the electronegativity difference between the atoms that are in the bond, and the molecule type is by its shape, whether it's symmetrical or asymmetrical. The first example we're going to look at is diatomic oxygen. For bond type, this is a nonpolar covalent bond because the electronegativity difference between the two oxygen atoms should be 0, because if it's the same number subtracted, it should be 0. The molecule type is also nonpolar because it is symmetrical. Remember, even though we draw these models in 2D, they are actually 3D. To address this, scientists have developed a shorthand that looks like this. When we draw methane, we show it with the 4 H's around the C like that. Later on in your college careers, you'll see this kind of model where there's a dashed line and a solid line. This represents the bonds going back into the space and kind of out of the 2D space. The ones with just the solid lines are in the plane of the paper. Here, the bond type, since we have all carbon to hydrogen bonds, it's going to be the same, but these bonds are all polar because they have different electronegativities. Carbon has a higher electronegativity than hydrogen does. Now for molecule type. Because the electronegativities are different, the atoms will have partial charges assigned. The atoms with the higher electronegativity will have a partial negative charge, and the atoms with the lower electronegativity will have the positive charge, resulting in a molecule that will look like this. So now carbon's going to have a partial negative, and each of the 4 hydrogens will have a partial positive. However, because all of the bonds are the same, the pull in towards the carbon is equivalent for all 4 hydrogens. When we show a dipole direction, we normally show it pointing towards the negative because the electrons are being pulled towards that particular atom. So Here you'll see that there we have little arrows that are all pointing in towards the carbon because each hydrogen is kind of losing control of its electrons a little bit towards the carbon. In symmetrical molecules like methane, the poles or dipole moments basically cancel each other out, resulting in an overall neutral molecule or a nonpolar molecule, because there ends up being no area of charge on the molecule. Now here's another example with HCl. For the bond type, again you want to look at the electronegativity difference. Molecule type, you want to look at the shape. This bond is going to be polar covalent, and this molecule will be a polar molecule. It's a polar covalent bond because H and Cl have different electronegativities. It's a polar molecule because even though it's a linear molecule like oxygen, there's no canceling of the dipole moment because it's a polar bond. So the chlorine has a higher electronegativity than the hydrogen, so it ends up being partially negative, hydrogen partially positive. And there's nothing on the other side of the chlorine to cancel out that pull towards itself. Because of that, it will be a polar molecule. So now I have some more examples for you to try. I'm going to put the example up, I'm going to wait a minute, and then put the answers up. So you should pause the video and try it on your own. Do not just play it through, you need to actually make sure you can do this on your own. So I'm looking for you to determine the bond type and then the molecule type. You may also want to try your hand at drawing the dipole moment, meaning which way is the general charge going to be traveling. We always go towards the negative. So our first example is CO2. The bond type here is polar covalent, and the molecule type is nonpolar because the two oxygens have a greater pull on the electrons, but because it's equal and opposite, it will cancel itself out and end up being a nonpolar molecule. Second example is ammonia. So for ammonia, I showed you both the appropriate shape, meaning with the H's pushed down a little bit due to the lone pair, and just a regular shape. Unless they specify, I believe either one should be acceptable. Here the bond type should be polar covalent because N and H will have different electronegativities, and the molecule type will be a polar molecule. It's going to be a polar molecule because the electrons are all being pulled in towards the end because it has the partially negative charge, and so it's just going to continue in that direction. There's nothing to cancel it out on the other end. Third example, okay, now here we have a little trick. There's two different bond types here. There's a C to Cl bond and a C to H bond. So you have to do each separately. So again, you're going to think about the electronegativities and then determine whether the bonds for each of those should be polar or nonpolar. Both of these should be polar covalent because there should be a difference in electronegativity between the C and the H and a difference in electronegativity between the C and the Cl. For molecule type, this is going to be a polar molecule. The electrons are going to be pulled in towards the carbon and then also up towards the chlorine because it's got the highest electronegativity, so that's going to end up being a polar molecule. Next example is water. The bond type here is going to be polar covalent. Molecule type is also going to be a polar molecule. Again, the O has the higher electronegativity, so it's going to be partially negative. H's are partially positive. There's nothing to cancel it out on the other side, so the dipole moment will go up through the O. Next example. Again, here you're going to have two different bond types, C to H, and then the C double bonded to the O. Both of these will be polar covalent because there's a difference in electronegativity between the atoms. And the molecule type will also be polar. The oxygen, again, has the highest electronegativity, so it's going to be pulling the electrons up towards it, nothing to cancel it out on the other side. Two more examples. There's a lot of different bond types here. We have a C to H bond, an O to H bond, a C to O bond, a C to double O bond, and then a C to C bond. Everything except the C to C bond is going to be a polar covalent bond because there's differences in electronegativities, some more so than others. But the C to C bond is going to be a nonpolar covalent bond because there is no difference in electronegativity between the two carbons. Molecule type is going to be a polar molecule, and the dipole moment should be kind of going off between the two O's because that's where the greatest electronegativities are. So that would be where the pole will be. And last example. Here again, bond type is going to be just one type of bond, Br to F. That's going to be polar covalent because there is a difference in electronegativity. Molecule type would be polar, and the pole would be going towards that one fluorine that doesn't have anything balancing it on the other side. It's got that lone pair instead. All right, now that we're experts in determining whether molecules are polar or nonpolar and where the dipole moment will be, we're going to need to talk about the different types of intermolecular attractions. The weakest forces of attraction between molecules are called London dispersion forces. This force is caused by the movement of electrons around the nucleus. At some point, or points in time, there will be a pileup of electrons on one side of the atom or molecule, resulting in a momentary non-symmetrical electron distribution, which creates a temporary dipole or an instantaneous dipole. An example of that is with the helium atom. Helium has 2 electrons. If by chance both electrons end up on one side of that atom, you'll create an instantaneous dipole, where one end of the atom will be a little bit negative and the other end will be a little bit positive. When that happens, it can induce a dipole in a neighboring helium atom, which will result in an attractive force. And this is what allows noble gases to form liquids and eventually solids. These instantaneous dipoles can induce or cause a dipole in another atom or molecule, which then allows an attraction to exist between the two particles. These attractions are usually only momentary and are very weak. However, they can become more important as the size of the atom or molecule increases because there are more electrons present, and therefore an increased chance of these momentary dipole interactions. These attractions are most important for nonpolar molecules because they don't have any other type of attractive force, but they're present in all molecules and atoms. So these are always there. It's just when you have a larger attractive force, it kind of overwhelms this one. Here are a couple examples of this just to show you again. So we have a helium atom. You can see in letter B how the electrons kind of get pulled to one end, which creates the partial positive, partial negative charges. And then you have the attraction that can occur between the partially positive end of one atom for the partially negative end of the other. The same thing will occur in a molecule, which is down at the bottom. So if you look at your hydrogens, your diatomic hydrogens, you again have that instantaneous dipole occurring, which induces the dipole in molecules nearby and will cause an attraction to occur between molecules. But again, these are momentary, instantaneous, and won't be very stable. Some examples of why this is important. So here we have a graph that shows the boiling points of different alkanes. We have methane, ethane, propane, and butane. Meth has 1 carbon, eth has 2, propane has 3, butane has 4. These 4 things are all symmetrical and have all carbon-hydrogen bonds, so they're nonpolar molecules. If you look at this, the trend observed for boiling point versus mass. As the mass increases, your boiling point also increases. Why is this happening? The more electrons you have, the more you are going to be able to induce these momentary dipoles, and that will allow for a greater attractive force. When your attractive forces increase, that makes it harder for you to boil or to evaporate your substance, and that's why the boiling point increases. So again, the greater the intermolecular attraction, the higher the boiling point should be. Down at the bottom it says which noble gas has the highest boiling point. Well, which noble gas would you guess would have the highest boiling point? The smallest noble gas or the largest noble gas? So to introduce dipole-dipole attractions, we're going to take a look at some examples. If you look at the table below, we have some alkanes and then alcohols. The only difference between the alkane and then the subsequent alcohol is the addition of a hydroxyl group to replace one of the hydrogen atoms. Why does this make such a huge difference in the boiling point? If you look at methane, it's negative 164. Methanol is 65. That's a huge difference in boiling point. The main reason has to do with the structures. So if you look at methane, it's got polar bonds, but they're symmetrical, so that's going to be a nonpolar molecule. If you look at methanol, now that's going to be a polar molecule because that oxygen and hydrogen group are going to pull the electrons towards them. Based on this experimental evidence, it is clear that polar molecules will have a stronger intermolecular attraction than nonpolar molecules. Now the question becomes, why? Why does that happen? If you look at this diagram, you can see that you have your partial positive, partial negative charges there. And then the dashed lines there represent the intermolecular forces between the dipoles, and the negative end of one molecule will be attracted to the positive end of the other molecule. These attractions work essentially the same way as in London dispersion, but because these are polar molecules, the dipole is a constant, so the attraction is permanent and will therefore be much stronger. If you think about the van der Waals or London dispersion forces, they're not permanent. Those electrons can shift around again, and that dipole that was created will be destroyed. In a polar molecule, that dipole is always there, and it's going to be a much larger difference between the positive end and the negative end of the molecule, so it's going to be a much stronger attraction. The next thing we have is a graph of the boiling point of hydrides of group 14 through 17. So you'll see they kind of go up. So CH4 is group 14, NH3 is group 15, H2O is group 16, and HF is group 17. Since elements in a group bond similarly and therefore have similar shapes, one would expect to see trends in things like boiling point and melting point. However, in looking at this graph, you can see that only group 14, the CH4, SiH4, has an expected trend. It kind of slowly increases. The other groups all start at their highest and then come down and then go back up. So why does that happen? The other groups all have polar molecules. So the group 14 is the only one with nonpolar shape. Okay? The rest of them are all polar. But you would still expect to see a trend, at least among all the polar things. What this graph says is that the attractions are strongest with the first element members of each group. This tells us that the dipole-dipole attractions must be very strong with these elements and hydrogen. These exceptionally strong attractions are referred to as hydrogen bonding. Now, hydrogen bonding is not an actual bond. There is no sharing or transferring of electrons. It is simply a very strong attractive force. The molecules that are hydrogen bonding can still move away from each other. So here we have the example of water again. That dashed line between the O of one molecule and the H of the other represents the hydrogen bonding. The hydrogen bonding is again not a constant force, but it is a strong force of attraction. Hydrogen bonding only occurs with molecules of ammonia, water, and hydrogen fluoride. Why those three? Why those particular things? Nitrogen, oxygen, and fluorine have the three highest electronegativities and will therefore have the greatest uneven charge distribution in a bond with hydrogen, which leads to really large partial charges and therefore the largest dipole moment, which makes for very strong attractions. So hydrogen bonding is exactly the same as dipole-dipole attractions, except they're just very, very strong and therefore have a greater impact on the properties of the substances. Here we have a summary of intermolecular attractions. So the first thing you should look at is the type of dipole formed, meaning is it a nonpolar thing or a polar substance. If it's a nonpolar substance, that's going to be an instantaneous or an induced dipole, and that's van der Waals forces or London dispersion forces, and that's common to all particles. If you have a permanent dipole, meaning it's a polar molecule, then you're going to have dipole-dipole forces, and you could include hydrogen bonding in that if it's a molecule that has hydrogen with nitrogen, oxygen, or fluorine. One last thing. So far we've just dealt with covalently bonded molecules, but we all know that if we add sodium chloride, an ionic substance, to water, it's going to dissolve. So what's going on? Remember, for things to be soluble, they must be alike enough in terms of their polarity. And ionic substances can dissolve in polar solvents because they both have charges, which allows them to be attracted to each other. So we have our picture up here, which shows a positive ion and a negative ion. The positive ion would be attracted to the negative end of a polar molecule, and the negative ion would be attracted to the positive end of a polar molecule. Here we have an example with sodium chloride. So the crystal lattice of sodium chloride will be broken apart by water because each of the oppositely charged ions will be attracted to and surrounded by the oppositely charged ends of the water molecule. This slide shows a summary of the types of intermolecular forces and goes through all the different types. So there's got a little question and answer scheme, which I thought was kind of handy. It might be helpful for you guys in determining which types of forces are involved. So I'll let you take a moment and look at that. This next slide gives you some properties and characteristics of the different types of substances and what kind of intermolecular forces they have. This I thought was also kind of a nice summary. You might want to jot this down in your notes as well. And I liked these two things that illustrated what happens when you mix things together. So take a moment and read through them. I just thought it was kind of a cool way to look at them, so I'll give you a minute for that. So this is the end of Review 3. We'll be working on some worksheets and problems in class. Please be sure that you have taken notes about this information so you're prepared in class. The information shown here is at the beginning of Chapter 10. So if you want to take a look at that and read and outline that information, that would probably be very helpful for you as well. Okay, good luck.